Hey everybody, in this next video lesson, I'm going to talk to you about a way to measure concentration that's different from molarity. There needs to be a different concentration calculation because molarity, frankly, has some issues with it. The first thing that I want to talk about is how molarity is very helpful in academic chemistry. It's very useful for stoichiometry because it can compare moles of a substance to liters of solution. And so molarity, as I like to say in other chemistry courses, is very useful for academic chemistry, but for practical chemistry, it's not that great. Mostly the reason that it's not great for practical chemistry is because the volume of a liquid is dependent on the temperature, and thermal expansion and contraction can cause the liters of solution to be different at different temperatures. You might not have noticed this in the past, but take 10 milliliters of water at room temperature and warm it up, and it will actually occupy a larger volume at a warmer temperature, even though you didn't add any extra substances in. So thermal contraction and thermal expansion is not great when you're talking about molarity. So if we ever need to measure concentration where temperature is not dependent, we need another way to measure it, and that is what is called molality. Molality looks a lot like molarity. It is a ratio, just like molarity, and moles of solute is on the top. But what's different about it is that instead of liters of solution on the bottom, we're looking at the kilograms of solvent. So moles and kilograms are independent of temperature change. In other words, they are not affected by temperature changes. This particular calculation of concentration is used to calculate boiling point and melting point changes in solutions in what is called a colligative property. We're going to be talking about colligative properties at a later date. But we need to know what molality is before we can calculate colligative properties. The abbreviation for molality is lowercase italicized m. Now there are a lot of m symbols in science, m for meters, capital M for molarity, so we need to keep them separate from each other. And this one is a lowercase italicized m. So whenever you see that, what that is referring to is molality, or moles of solute per kilograms of solvent. So in a practice problem like you see right here on the screen, you will have either moles or grams of a solute, that is what's getting dissolved, in this case it's NaCl. We need to convert the grams to moles, and then we're going to divide it by the kilograms of the solvent. So we need to establish what the solvent is. It's water, and I have grams or kilograms of water. Sometimes you might have volume of the solvent, and you would need the density then to convert to kilograms. And so it's an easy calculation. Remember, molality is equal to moles over kilograms. So we just simply need to take 25 grams of NaCl and divide by the molar mass to 58.44 grams on the bottom, moles on top, and then we got the number of moles. Then we need to take the grams of water and we need to move the decimal point over 3 to the left, so we have 0.250 kilograms, and then we just need to simply take these two numbers and divide them, and you have the molality. When you do this, you get a molality of 1.71 molal, or moles per kilogram. So hopefully now you see why molarity has some problems with it, and because of that we have something called molality, which sounds a lot like molarity, and I understand the confusion, but it's important to keep them separate. But molality is moles per kilogram of solvent. Well, that takes care of this video lesson. Thanks for watching.